Okay, everybody, we're moving on to something a little bit further um, called types of artificial radioactivity. So we looked at artificial radioactivity as taking a target nucleus and then firing a particle at it and then causing some type of change. So what we do is we move on to two types of artificial radioactivity. One is, kind of natural. I guess if you did it on Earth, it would be artificial. So the first one was is something called fission. All right, and you fast forward back, after Rutherford did his experiment with changing nitrogen into oxygen, scientists begin to do some experiments with um, hitting nuclei with particles, and they stumble on this interesting reaction where we take a large nucleus such as uranium 235, and basically what we do is we split it. All right, so we fire neutrons at it, and when scientists fired the neutrons at it, they realized that they ended up splitting the nucleus. Okay, and what they ended up getting was this release of energy. All right, so the reaction is what we see here. Is if I could get my pen, I will show you. Okay, and what we'll see is you take a uranium 235 nucleus, and what happens is the neutron it beds itself into the nucleus, and what that does is it splits it into two main pieces, splits into a barium and a krypton. And what happens is then releases three additional neutrons. So one neutron is emitted. I'm sorry, not one neutron is used to hit it, and then three neutrons are produced at high speeds, and then a lot of energy is also emitted too. And this energy is really what we want to look at, because that it becomes the energy that we can use for good things and bad. We can use this for a nuclear power plant, or we can also use it for nuclear warfare. Right, so some things about this also is important to know is that once this breaks into these two pieces, this is really the nuclear waste that we hear about from nuclear power plants and from nuclear explosion. Why it's so dangerous is that the leftover pieces here, after they create the energy, these are radioactive isotopes that are highly unstable and highly dangerous as they emit their own radiation. All right, so basically in a fission reaction, you get two to three released neutrons, okay, which again will make this reaction continue, right? These guys can actually shoot out and hit other uranium 235s. The process can continue, okay. And what this since this can continue, okay, and those can hit other uranium 235s, which continue the process. We call that a chain reaction. Again, a reaction that continues to hit other nuclei. And we'll see this a little bit more in the next slide. Okay, we can use this in nuclear power plants. Okay, and we can also use it in nuclear weapons or nuclear bombs. Okay, the fission products are highly radioactive. These are nuclear waste products. Okay, and they're radioactive not only for long periods, but also, again, really releasing this radiation. And this poses definitely a storage problem and a health hazard to the people who use it. So, again, whether you're making a bomb out of this or whether you're using a power plant, you're still going to be producing this nuclear waste that has to be, in a case of a bomb, I guess you want it to be dangerous, but, in a nuclear reaction, in a power plant, you're going to make sure you have to take this waste here and make sure you put it away and store it and keep it away from people. All right, so here's a little cartoon of it, and you can see this neutron is going and going to hit this uranium 230. I could give you a little black pen here. Okay, you can see this neutron goes into this nucleus. It gets embedded there. You can see it becomes temporarily uranium 236 because you're adding the neutron to it. But this can't be stable. And what happens eventually is this will separate into two particles, and then these neutrons will be, ejected at high speeds outward. Again, these can go and restart the process. All right, so that would be fission. Again, we'll look at it a little bit more closer next slide. And what we do is we compare this to the exact opposite. And the exact opposite can also be a nuclear change that can be done, in this case, artificially and also naturally in the stars. So where fission is the splitting of a nucleus, a larger nucleus, the reverse of this is fusion. Okay, so when you fuse things together, you combine lighter nuclei or smaller nuclei to form larger nuclei. Okay, and again, both these processes will release a large amount of energy, so it makes them very attractive for alternative energy sources. Okay, so what we're going to do in this case is we're going to take two isotopes of hydrogen, and you're basically going to mash these together. We're going to take these guys and combine them. Okay, and then we're going to make helium. Okay, and we're going to release a neutron and some energy. All right, so again, what's attractive about this is where in fission you get nuclear waste, you get no nuclear waste in fusion. All right, so it makes it a very attractive, way we can do this. But where there is no nuclear waste, we have other problems. All right, so this occurs naturally in the sun, in the cores of sun and stars. Okay, and nuclei repel each other. So because of the problem of combining these guys, again, these nuclei, again, that's one proton, and this is one proton, and we have to get those protons to combine, which is hard to do. Okay, we're going to have to put this under very, very high temperature and very, very high pressure. So we're going to compress this. We're going to really push them together under very high temperatures, force those particles to collide with high kinetic energy. But this can be done in the core of the sun because the sun is very hot. On Earth, this is very difficult to do because it's very difficult to get to the high temperatures and pressures needed to do this. All right, so again, take a look down here. You'll see deuterium. Now, don't worry too much about the words here in deuterium. Deuterium is simply the name of hydrogen when the mass number is 2. And tritium is when you have hydrogen with a mass number of 3. So the deut in the beginning means 2, and the tri means 3. So if you put these two guys together, and you can even see it here, you could see one proton and a neutron here. And when you fuse these, again, very high energy is needed to do this. You get a helium plus the neutron. Okay, and then energy is emitted. So again, can we use this energy for something? And the answer is yes. Right now, fusion reactors are just really theoretical. They're actually scientists have attempted to, build these things, but they're very difficult and they don't work all that efficiently. All right, so just take a little bit closer look at the chain reaction. Okay, and what we see here in the chain reaction, okay, is taking this uranium 235. Okay, and what we find is that we're going to have to use uranium 235, or you can use plutonium 239. These are the only really two isotopes that are going to do this. So what you can take a neutron, this neutron is going to be fired into some critical mass, and that simply means becomes the smallest piece of fission, smallest piece of uranium 235 that can be used. Okay, if you use too small a piece, so for example, if you have a chunk of metal, that's a chunk of this stuff that's too little, then this won't work. So you have to have this this big enough piece that it will work. So we call that piece a critical mass. Okay, so then what we're going to do is we're going to add this neutron to this. It's going to get very unstable, and then it's going to begin to split. You can see it splitting. And what happens as a result is we get two smaller nuclei. This causes an energy release because you're creating a small nucleus, right? So when we talked about, attractions formed, you talk about very strong attractions here, okay? And then you create possibly a krypton nucleus and a barium nucleus. Again, these pieces are not always the same. They can be slightly different, and that makes this that much more dangerous because sometimes we can't predict what we're going to get, and that becomes your waste. All right. And as a result, we get 3 more neutrons. Now, these are high-speed neutrons. I mean, they're emitted because of the energy. This energy heats them up and causes them to fly out at high speeds. And what do? They hit other uranium-235 nuclei and plutonium-239 nuclei. Okay, and again, this will eventually go into this guy just like it did in the beginning. Okay, and again, we're going to get more splitting with more neutrons and so on. You can see how this thing begins to spread, okay, as you create this thing. Now, if you allow this to take place uncontrolled with several, you know, kilograms or grams of this stuff, which is many moles, you get quite a large explosions. And again, this takes place in pretty much a fraction of a second. So, so a chain reaction takes place in fractions of seconds, generating massive amounts of energy. Okay, a massive with using actually a very small amount of fuel. Okay, nuclear waste products are very, very highly radioactive and dangerous, and the elements formed are very unpredictable. And again, storage of these kind of things is very difficult to do. Really, what they do in power plants these days is just store them in underwater to block some of the radiation, or they can put them in these big concrete, steel, and lead containers, which then they just have to stack up and let them sit. Okay, so that becomes the essential part of an uncontrolled or a chain reaction. Um, and we can go to the next slide so we can see how this is going to be used. Now, what we can do is we can take fission, and scientists have learned how to control this. So if you want to control fission, okay, you could simply put it in something called a nuclear power plant. And again, don't get crazy with this. It's not something you have to know every part of the reactor, but you just want to be, familiar with how they actually work. So basically, there's fuel rods, and these fuel rods are is the uranium 235 that you need. Okay, and typically it's 235, or it could be plutonium 239. So you can either use uranium 235, okay, or Pu 239. Okay, and that will be made in these fuel rods, and that'll be put into a core, and this will be surrounded by concrete and lead. So concrete and lead, this is what this container is made of. So again, that's going to be in here. That's where all the fission is going to take place. Now, in between these things, typically, are called control rods. And what the control rods do is the control rods simply absorb the extra neutrons that are given off when fission takes place. So again, you would have fission. You would have all these neutrons flying around, hitting other uraniums, causing more fission. But if you can control the number of neutrons coming out of this, okay, then you can control the speed of the reaction, and you can slow down this reaction and produce energy much more slowly. All right, and again, don't worry about this extra molten sodium or liquid water under high pressure. Simply, what you're doing is you're causing a lot of heat to build up in here. The heat will drive the steam. The steam will end up driving this thing called a turbine, and this turbine will end up creating electricity. All right, and that's really what you want to do. And then eventually, this cold water from the steam is cooled, and then you're allowed to cool it. And then what they do is they bring warm water away and they bring cold water back in here, and they just circulate the water. So really, what you're doing is using this is a steam generator to turn for electricity. The key is you have very little fuel that creates a lot of energy. So energy from fission is typically, um, again, converted to electricity, and this is going to power homes, industries, and businesses. Okay, and basically today's nuclear power plants are extremely safe. They've actually increased the technology really well on these things, but the risk of a meltdown or risk of this getting out of control still exists. If this should crack open or there should be some damage to the reactor, while there are a lot of safeguards in place for this, we still have instances in history where we've had problems with nuclear reactors. Okay, the only thing that still is a problem is the storage of these hazardous fuel rods and the waste. So once these fuel rods are used up and they no longer have enough uranium in them, they're basically spent. They call them spent fuel rods, and those have to be recycled. They have to be restored. They have to be usually placed underwater and before they're recycled, and it becomes a really big, problem to do. And again, it's very highly dangerous work. Um, basically, the most notable nuclear power plant disasters include Chernobyl, and it's in Russia in 1986. I'll put up some videos on this, and we'll see them in class. And for the remote students, I'll also make this available for you to watch. Okay, due to some human error. It wasn't just human error, but it was a lot of human error involved in this thing melting down, basically in Chernobyl, in Russia. Okay, and a little more recently was in 2011 along Japan's coast. They have several reactors, and there was an earthquake off the coast in the water in the water off the coast. Okay, where there's some trenches and some volcanic activity, and that created a tsunami. Again, that went and basically flooded out the reactors and really put them into real big distress. And that caused a radioactive spill also. So that was also a problem. Again, that wasn't really human ever. That was more of a natural disaster. But then we also have to think of terrorism too. Terrorism also is also a real threat around the world, and the countries who have nuclear reactors have to be very careful that they make sure they're guarded and safe. All right. In an uncontrolled fission reaction, this is where we can actually be fairly destructive with this in a nuclear bomb. And again, you don't really necessarily have to know all the parts of this. It's simply just the technology and really how it works. So basically, scientists take a critical mass of this fissile material, this plutonium material, and then what we ended up doing is we end up going. What we do is we take a piece of material that will undergo fission, and what we do is we use a chemical explosion to form a mass of this plutonium or uranium. Okay, and we drive together two pieces to create a critical mass, and then we initiate fission. So in an atom bomb, if you take a look over at the picture, we could see we have again, like I said, you don't have to know like the parts of this, but basically you have a neutron initiator, which simply starts the chain reaction going. Okay, and then you have this core here of this fissionable material. It could be uranium or plutonium. Okay, and then you have this you know um, you have this shock wave kind of material that surrounds this. So this allows this thing to simply just explode outward and produce all the energy needed for this. And all of the nuclear waste is actually spread out over the whole land and water and sea, and actually makes a pretty big mess. So we want to, again, not really use these things, and we want to prevent other countries from using them too. This is the kind of bomb that was dropped on Hiroshima and Nagasaki during World War II to end World War II, really. All right. The hydrogen bomb is a little bit different. The hydrogen bomb simply uses a chemical explosion that actually allows fission to take place, and then that initiates the necessary energy needed for fusion. So this is even more destructive than a typical atom bomb. Again, it uses energy from primary fission to ignite a secondary nuclear fusion reaction. Okay, so there's a small atom bomb here that explodes. That initiates the hydrogen fuel in here. Okay, and this causes this thing to really go off. And you can see miniaturization is a big deal. You can make this a lot smaller. So hydrogen bombs can pack explosive power into smaller, lightweight packages delivered by missiles. So here's where we got to start being really careful. Where this could be a warhead that can be attached to a missile, and these days these things can track over oceans, and literally other countries can be hit without even leaving your country. You can send this across on a missile. So again, we really want to be careful with this. You really want to make sure that we're be careful, and we're not jumping the gun when it comes to using nuclear weapons. Any nuclear weapon that is used is a problem everywhere. We all live on the same Earth, so if anything goes off, it emits radiation. It can ruin landscapes everywhere. All right, so that's really a quick overview of fission and fusion. Again, uncontrolled fission would be an atomic bomb, where a controlled fission reaction would be in a nuclear power plant. And again, it's hard to do it here on PowerPoint with the lessons. Please take the time to look at some of the videos and watch some of the stuff I'll put up on Canvas. So at least you get an idea of what you're dealing with, and you can get a really good inside look at some of the politics of this in the past, and also what these things can actually do. It's worth the look at it. All right. So I will see you soon.